In this last section of chapter 1, we're going to be looking at subsequences and monotone sequences. So we'll first begin by defining what a subsequence is. First, we let a sub n be a sequence, and n sub k be a sequence of positive integers such that n1 is less than n2, less than n3, so on and so forth. The sequence a sub n sub k is called a subsequence of a sub n. So what a subsequence basically means is you get the original sequence and, well, you can just delete some terms and you'll have a subsequence. Also, I'd like to point out that a sequence is a subsequence of itself. So we can delete no terms and it's still a subsequence of itself. So here, this part confuses some people. So a sub n, the sequence, we have a sub 1, sub 3, so on and so forth. For a sub n sub k, the subsequence, we may delete some terms. So for example, we do have a sub 1, but now we're deleting a sub 2. We're deleting a sub 4. We have a sub 7, so on and so forth. So here, the positive integers n1, n2, n3 is 1, n2 is 3, n3 is 5, so on and so forth. Why? Because we're getting it from here, first term, the second term, third term, so on and so forth. That's what a subsequence is. We're deleting subterms of the original sequence, a sub n, and we're making a new sequence. Okay, so just to take a look at some examples, we're going to take a look at some sequences we've already seen before. So the first examples are 1 over n. We know exactly how that looks. And the subsequence of that would be 1 over k squared. Right, so all these terms of this sequence, the second sequence, are also in this sequence. But we just took out some and left, well, the ones that are in the form 1 over k squared. Another subsequence would be 1 over 2k, which deletes less terms, but again, all those terms are in the first sequence. So they're both subsequence of the first sequence of 1 over n. Another one is the sequence that goes from 0 to 1 to 0 to 1, so on and so forth. Just oscillates between 0 and 1. So we can pick out a subsequence such that we can have nothing but zeros. Right? We can pick the first and the third and the fifth, every odd number, right? And we'll have nothing but zeros. Similarly, we can pick every even number and we'll have nothing but ones. Right? And so down here, just to show you visually, we have the sequence 1 over n. From 1 to infinity. And if we were just to have the, for example, the subsequence, this subsequence here, 1 over 2k, we could just delete some terms of the original sequence. So for example, we would delete the first one because there is no 1. We would delete the third one. We would delete the fifth one. So on and so forth. And we still get a subsequence. A sequence that converges. Well, this one seems to converge to 0 as well. But we also get that sequence. Over here, same thing. We can just delete all these. I'm just going to scratch them out. And we can just be left with a sequence of nothing but zeros. And that would be a subsequence, right, of this original sequence. So last thing I want to point out here, this sequence we know converges to 0. That looks like a not 0. So we know that that sequence converges to 0. We know this sequence, it seems like it's converging to 0 as well. So does this one. But what about over here? We know this one diverges, right? Because it's not convergent. But this one seems to converge to 0, and this one seems to converge to 1. This leads us to our next slide. A sequence converges if and only if each of its subsequences converges. In fact, if every subsequence converges, then they all converge to the same limits. Right, and we got a little taste of that from the last slide. So we're going to have this to have a little picture. So first, the easy part, because this theorem is biconditional, we're going to have two directions. The first one, if every subsequence of a sequence converges, then the sequence obviously converges, since the sequence is included among the subsequences, all of which are assumed to convergent. Right, so we're assuming all subsequences converge, and because a sequence is a subsequence of itself, it also converges. That's the easy part. Now we're going to prove the other part, which is juicier, so to speak. So assume now that the sequence a sub n converges to a. Right, so I'm going to put a right here. And a sub n, I'm going to draw it in green. So let's say we have a point here, we have a point here, here, here. And then as we get closer and closer, there's a bunch of points. Right? And a sub n sub k, I'm going to put in purple. So we're going to show that this subsequence, a sub n sub k, converges to a as well. Right? So we're going to choose epsilon greater than 0. And since our sequence a sub n converges to a, well, there's a positive integer big N such that little n greater than or equal to big N makes the difference between our sequence and its limit point arbitrarily small, less than epsilon, right? That's just the definition of convergence. Okay, but now we have that since we have a subsequence of the given sequence, well, here these must be greater than or equal to k. And remember from the last slide where I said, well, take a sub 1, a sub 2, a sub 3, a sub 4 from the original sequence. Right? And the subsequence can be a sub 1, a sub 4, a sub 9, a sub 15, so on and so forth. Well, what this is saying is that this number here, this subscript, is less than or equal to the one above. Sorry, backwards. It's sorry, it's saying that this subscript up top, let me do it in red. This subscript is less than or equal to this subscript here. So 2 is less than or equal to 4, that fits. 1 is less than or equal to 1. 3 is less than or equal to 9. And why can't we just say it's less than it? Why do we have to have or equals? Well, because if we take the subsequence that's identical to the sequence of itself, the original sequence, well, then we get that all the subscripts are equal to each other, right? 1 is equal to 1, 2 is equal to 2, 3 is equal to 3, so on and so forth. But we know k is less than or equal to n sub k. What does that mean for us? Well, that means that if we have k greater than or equal to n, well, it certainly means that n sub k suffices for a convergence, right? So if n sub k is greater than n, we get that the difference between a sub n sub k and its limit point, a, is less than epsilon. So up top on the real line, I'm going to use purple for the subsequence. Let's say we include this point here. We include this point in the subsequence. This one, this one, so on and so forth. And a bunch of points. We have infinitely many. Well, if if n sub 50, here's as an n, suffice to show that it was within epsilon of a. Well, if we were to choose k as 50, then n sub k is going to be greater than our n, which was 50. I'm going to put it in green. Then this 50. So it certainly suffices as well for it to converge. So therefore, our subsequence also converges to A. So note that if every subsequence of a given sequence converges, then the sequence here's the typo, converges as well. And by the argument just given, all subsequences converge to the same limit because we got an arbitrary subsequence and it converges to A. So all subsequences converge to the same limit, which in this case is A. Okay, so now moving on to our next theorem. This is going to be a lemma because we're going to use it to prove the theorem. And it says, let A sub n be a bounded sequence of real numbers. So if A sub n is a bounded sequence of real numbers, then A sub n has a convergent subsequence. Right, so for example, the one that would go from 0, 1, 0, 1, that's a bounded sequence. And if we just pick nothing but the zeros here, every other term, we get a convergent subsequence. So that's a neat lemma we're going to use for this next theorem. This next theorem says, suppose x sub n is a bounded sequence if all its convergent subsequences have the same limit, then the sequence is convergent. So first, we draw the real line, and we're going to do the easy part. Since it's I should say easy part. So, but first we're just going to assume that all convergent subsequences of x sub n have the same limit, and we're going to call it x naught. Then the lemma, we just saw, guarantees that there's at least one convergent subsequence, right? Because all these subsequences are convergent, so they're bounded. So there must be one convergent subsequence. So to explain that, let's just say this is x naught. And we're assuming that all subsequences x sub n sub k have the same limit, which is x sub naught. The lemma above guarantees that there's at least one convergent subsequence. From here, we're going to go with proof by contradiction. So we're going to first say that if x sub n does not converge to x naught, well then, just using the definition, there's an epsilon greater than 0, for which, so say this is our epsilon neighborhood. That is an epsilon neighborhood so small that you can't find an integer n to satisfy the definition of convergence, right? Such that x sub n minus x naught is less than epsilon. You can't find this point, right? There exists no n. N doesn't exist. And that's the case if x sub n does not converge to x naught. So if we try n sub 1, then there is n1 greater than 1, such that the difference between that term and the limit is greater than or equal to epsilon. Right, so we can do the same thing for n sub 2 greater than 2. such that, again, it's greater than or equal to epsilon. And we can just continue this, right? So we continue this sequence n sub k recursively. We find that for each positive integer k, there's an integer n sub k such that the difference between that term of the subsequence minus its limit point x sub 0, or what we should get as a limit point x sub 0, is greater than epsilon, greater than or equal to epsilon. Well, the sequence x sub n sub k being bounded will have a convergent subsequence, right? And that will be convergent. That will be a convergent subsequence of the original sequence, but that will not converge to x naught. And this contradicts our hypothesis, therefore showing that this is false. So x sub n must converge to x naught. Now we're going to define, I guess, go on to the easier stuff. If you need to read the proofs, maybe a bit confusing with the whole definition of subsequence. So make sure we digest it. We're going to be moving on to the definition of increasing, decreasing, and monotone sequences. So sequence a sub n is increasing if and only if a sub n is less than or equal to a sub n plus 1 for all positive integers n. Decreasing, the same thing, just the inequality flipped. And monotone, sequence is monotone if it's either increasing or decreasing. And it's really similar to increasing, decreasing monotone functions. So over here we have functions, increasing function, decreasing function. Sequence, basically the same thing. If we had a sequence like this, that's increasing. Every term we go up, every n that we go up, we get a larger number. Decreasing sequence would just be going down, so it's the same concept as with functions. Here we have a constant function. This one is also monotone because it's both decreasing and increasing by definition over here. I know that can be a bit confusing, but we have a weak inequality that makes this increasing and decreasing sequence. But it's the same concept. So now we have a theorem that says a monotone sequence is convergent if and only if it is bounded. Right, so again, by conditional, we're going to have two directions. And hopefully this real line can help us for this proof. So first, we're going to suppose a sub n is a monotone sequence. Right, so it can be either increasing or decreasing, but not both. Actually, I take that not both back because it could be constant, right? But we're just going to assume it's a monotone. We know what that is. And it's bounded. And for this case, we'll just suppose the sequence is increasing. For decreasing, it could be a similar reasoning. But for this case, we're just going to assume suppose the sequence is increasing. Well, the set a sub n is bounded. Right, so we're going to let the s equal the supremum of all the terms of the sequence. And we're going to show that that converges to the supremum. The sequence converges to the supremum. So, actually, before moving on, I guess I should draw some pictures to help out. So we have a sub n. And let's see, over here we have our supremum s. We have a bunch of points here. Sorry if some don't appear to be dots. They're just terms of the sequence a sub n. We're going to show it converges to s as it is monotone and bounded. So choose epsilon greater than 0. Since s is the least upper bound of all these terms, well, s minus epsilon, which would be somewhere here, s minus epsilon is not an upper bound, right? So that means, say, s minus epsilon is right here. So there's an n naught such that there's a sub n sub naught term of the sequence somewhere in between, right? Such that it's greater than s minus epsilon. Well, for n greater than n naught, s minus epsilon, we know, is less than that term of the sequence, the red dot we have on our real line, which is less than a sub n, again, because we have that n is greater than or equal to n sub naught. And that is less than or equal to s, because s is our upper bound, which is obviously less than s plus epsilon. Right? So, I should probably delete this. But that means that a sub n therefore converges to s. Why? Well, because this a sub n sub naught, we can keep getting it closer and closer, right, to s. But a sub n will always be closer to s than a sub n sub naught. So it's getting within that epsilon neighborhood of s minus epsilon and s plus epsilon, showing therefore that it converges to s. For the case in which a sub n is decreasing, like I said, let s just be the infimum of the sequence, and all the details are pretty much the same, just flipped inequalities, and you should get the same result. Because it's biconditional, we do the other direction, which says if the sequence is convergent, well, by a previous theorem we saw, was it the first lesson? I believe it was 1.1, that if the sequence is convergent, then by a theorem in that section, the sequence is bounded, which shows both directions now. So a monotone sequence is convergent if and only if it is bounded. So let's take a look at these two sequences. Well, in this case, our sequence is increasing, so it is monotone. So why doesn't it converge? Well, because it's missing the boundedness, right? It's not bounded because this sequence just keeps going on. To infinity, it diverges. So that's why the sequence does not converge. Or it's another reason, or it's another way to show that it doesn't converge, since it is monotone, but it's not bounded. Over here, we do have boundedness, right? It's bounded between, I can bound them between, I don't know, -1 and 1.1. So this sequence is bounded, but what is it missing? It goes up and down and up and down. So it's not it's not monotone. So this one is bounded, but it's not monotone, so it also does not converge. Okay, moving on to our last result for this section. We let E be the set of real numbers. Then X sub naught is an accumulation point of E. If and only if there is a sequence X sub n of members of E, each distinct from X sub naught, such that X sub n converges to X naught. Okay, a real line to help us with the visual again. And here comes our proof. So in this case, we're going to let X sub X naught be an accumulation point of E. And for E, I suppose I'll just do this case. This is our set E, that interval of the real line. I don't put in numbers because, well, it can just be anywhere on the real line. Okay, and you know what? For the heck of it, I'm just going to delete some of this line because maybe we don't want to include all the points of the line. So I'm just going to do it like this. So all those points are deleted from our set E. E is that set. And we're going to let x naught, in this case here, be an accumulation point of E. Notice how there's points to the right and to the left of it. Well, then for each positive integer n, there's a point x sub n of E such that 0 is less than the difference between x sub n minus x sub naught. And we're going to let that be less than 1 over n. Right, so in the parentheses here, let's do this. And we're going to put x sub n right there, x sub n. The difference between those 2 points is less than 1 over n, right? Because we have the neighborhood x naught plus 1 over n. And I'm just going to put it up here, x naught plus 1 over n. Minus 1 over n. Minus 1 over n. So now we need to show that x sub n converges to x sub naught. Right, so we're just going to choose epsilon greater than 0. Then there's a positive integer n, such that 1 over epsilon is less than big N. Just as the proofs in section 1.1, we show that the difference between the points x sub n minus x sub naught are less than epsilon, therefore converging. Right, so therefore x sub n converges to x sub naught, x naught. Right, so we can get a sequence in this interval that converges to x naught. And now, since it's biconditional, we're going to suppose now that there's a sequence x sub n of members of E, each distinct from x naught, that converge to x naught. Well, since every neighborhood of x naught contains all but a finite number of terms of the sequence, well then every neighborhood of x naught must contain at least one member of E that is distinct from x naught. So what does that tell us? That tells us that x naught is an accumulation point of E by definition. So again, maybe to digest it, I know we had several theorems, I think 4 theorems, not the easiest of the chapter, but if you've been watching all the other lectures, you should be able to, read them, maybe stare at them for a while, but you should be able to understand everything that's going on. And that should conclude our section. Just some things I want to point out. For example, your professor might ask you to show that a sequence is convergent. We can use the theorems in this section. For example, showing that we can somehow get the sequence if it's a tricky one. I don't know, something like s sub 1 is equal to square root of 2, and something recursive such that s sub n is equal to square root of 2, let's make this longer, plus s sub n minus 1. That's a recursive sequence. So this is for n equal to 2, 3, so on and so forth. But we can actually show with some algebra that this sequence is bounded by 2. So n sub n is bounded by 2, and it's actually monotone. It's actually an increasing sequence. So if your professor asked you to show that that sequence is convergent, it may be a bit hard to use a definition, but we can definitely show with some algebra that it's bounded by 2 and it's monotone, therefore it is convergent, right, using our theorem. So that's the other things I wanted to point out. There's probably exercises in the Goggins Introduction to Analysis book that can be really useful. But that concludes this section, and we'll be moving on to chapter 2, where we talk about limits.